Hello, it's Mrs. Scarple here, and this is Lesson 3 from Unit 2, Building the Perfect Square. The reason we are going to be building perfect squares is because the process called completing the square is what we use to convert a quadratic function in standard form to vertex form to make it easier to graph. But before we get into the process of building the perfect square or completing the square, let's review the graphing that we did in the previous two lessons. We have y equals x squared plus 5. Looking at this function, you should be able to recognize that this is a shift of the parent function y equals x squared up 5 units. So our vertex is going to be 0, 5. It is also going to open up because we have a positive x squared, and we don't have any stretch or shrink because we don't have a coefficient other than 1 in front of x squared. So let's get our axes on our graph. And we can plot our points using anchor points, and we can move on. So our vertex is 0, 5, so up 1, 2, 3, 4, 5 is our vertex. The graph opens up. So keep in mind anchor points are 1, 4, 9. Unfortunately, I moved my x-axis up so high we won't be able to do the 9, but we should be able to do the 1 and 4. And what I mean is when we move horizontally 1 unit, we move 1 unit up. When we move horizontally 2 units, we will move 4 units up. And then because parabolas are symmetrical, we can do the mirror image on the other side. And here is our parabola. For our second graph on this slide, we see that it will shift down from the -3 and is going to shift to the right because of the x minus 1 squared. Keep in mind something that may help you remember which direction to shift it to. X needs to be a positive 1 if this expression is going to equal 0. So our vertex is 1, negative 3. This is also open up because it's positive in front of the item that's being squared. And again, we do not have any stretch or shrink. This time I will put my axis just a little bit lower. So 1, negative 3, that's 1 to the right, and down 3. We said there was no stretch, so we can use the 1, 4, 9 anchor points. So 1 unit horizontally is 1 unit up, 2 is 4, 3 is 9. And again, we have the reflection of those points on the other side of our oops, I got those over 1 too far. On the other side of what would be the axis or line of symmetry that goes through the vertex. And we have our parabola. Last one is 2x squared minus 5. So we're going to shift down 5. Notice we're not directly adding or subtracting from the x in this equation, so this also only has a vertical shift. So our vertex is 0, negative 5. The 2 is positive, so this is going to open up. But because of the 2, we have a stretch by a factor of 2. So let's get our axes on here. Plot our vertex, 0, -5, 1, 2, 3, 4, 5. So because we have this stretch by a factor of 2, those anchor points, the 1, 4, and 9, each need to be multiplied by 2. So 1 times 2 is 2. 4 times 2 is 8. 3 times 2, or 9 times 2, excuse me, 9 is 3 squared. 9 times 2 is 18. And I just barely got that on this graph. I'm going to draw the reflection for the symmetry. And then we have a much narrower parabola than the previous two. So, what's our focus in this lesson? To find the square of a binomial expression, recognize a perfect square trinomial, and create perfect squares from partial areas. We're also going to find relationships between terms in a perfect square trinomial. And how can we use models to find these expressions for perfect squares? So let's go back to Optima. Optima has a quilt shop where she sells many colorful quilt blocks for people who want to make their own quilts. She has quilt designs that are made so that they can be sized to fit any bed. She bases her designs on quilt squares that can vary in size. So she calls the length of the side for the basic square X. So I'm just going to draw a basic square X to build off of in our problem. And it has dimensions of x by x because it's a square. The area of the basic square is the function a of x equals x squared, and that's because we would take x times x to get x squared for our area. In this way, she can customize the designs by making bigger squares or smaller squares. So if Optima adds 3 inches to the side of the square, what is the area of the square? So here is our basic square, and she's going to add 3 inches. Is what is happening. So if we want the area of this square, just in terms of side length, like we did with the x squared, we're going to have an area that is going to equal x plus 3 squared. But if you notice, I didn't finish off the square here. That's what we're going to do in our following problems. So when Optima draws a pattern for the square in problem 1, it looks like this. So I had each of these are going to be 1 by x for a total of, so this would be a 1x, 1x, 1x. So we have 3 of them here. The area of this is x squared. This is also 1 by x, so we have 1x, 1x, 1x for another total of 3 by x. And then since each of these rectangles is only a unit wide, each of these squares is a unit square. So it's 1 by 1 by 1 by 1. So using the diagram and the equation a of x equals x plus 3 squared, explain why the area of the block square a of x is also equal to x squared plus 6x plus 9. And it's because in addition to x squared, we have 6 rectangles, each with an area of x. There are 9 unit squares. So if we add them all together, we'd have x squared for the square, a total of 6x for the 6 rectangles, and we have the 9 unit squares. The customer service representatives at Optima's shop work with customers and write up the orders based on the area of the fabric needed. As you can see from problem 2, there are 2 ways that customers can call in and describe the area of the quilt block. One way describes the length of the sides of the block, and the other way describes the areas of each of the 4 sections of the block. So for each of the following quilt blocks, draw the diagram of the block and write 2 equivalent equations for the area of the block. So remember, the x is our base square. So it's x by x. The side length is a +2. So I'm going to add an inch and an inch this way for the +2, and we'll add 2 inches on this side of it for the +2. But in order to finish the square, we need to fill in this corner, which is going to give us 4 unit squares. So our area, our A of x, if we just write it in terms of side length, is x plus 2 squared, because we have 2 sides that are x plus 2. If we do it in terms of area of each piece, we have the x squared for the main square, plus we have 1, 2, 3, 4 areas of x for 4x, plus we have a total of 4 unit squares. These 2 equations are equivalent. One is in terms of the side length, and one is in terms of the area of each region. If we take a look at a block with side length x plus 1, so we start with our basic square x by x, and then we add an inch to our dimension, but we need to complete our square. What I see right now is not a square. So to complete that square, we have to fill in the lower right corner, and we only have 1 unit square for this one. So our area in terms of side length is x plus 1 squared. Our area in terms of each of the different shapes within here is x squared plus 2x plus 1. So do you notice any patterns here? You might have noticed that when we add a length of 2, we end up doubling that for the middle term. So in the trinomial, a trinomial has 3 terms. So in the trinomial, the middle term is 2x times the length added. The third term is the square of the length added. So let's see if we can do some more of these. Here we're given some partial areas, and that's because Optima's dog Clementine, whom she likes to have around the shop, got a little hungry and started to chew up the orders. When Optima found the orders, one of them was so chewed up there were only partial expressions for the area remaining. So we're going to help Optima by completing each of the following expressions for the area so that they describe a perfect square, and then we're going to write the two equivalent equations for the area of the square. So if we look at our expressions, we see an x squared. Well, that's going to be our basic square. And then we have a plus 4x. Well, if we're going to keep the shape of the square, what we add onto each dimension has to be the same. So that means we need to divide this 4 by 2. So we can write our area in terms of dimensions as a of x equals x plus 2 squared. But then if we want to write the equivalent one, we need to finish this square. We need to include this lower right corner and find how many units are in that area, and that's 2 times 2, which is 4. So we'd have our square of x squared. We have 4 rectangles of area x, and we have 4 unit squares for an equation of a of x equals x squared plus 4x plus 4. If we take a look at B, starting with our basic square for the x squared, this time we have 6x. So if I'm going to divide that evenly on my two sides, I'm adding 3 to each dimension. So one area is x plus 3 squared. The other area, we need to complete the units that we end up creating for a total of 3 by 3, which is 9. So a of x is going to be the x squared plus the 6x plus 9. Now, you might think that drawing in all of these rectangles and all of these unit squares gets to be a bit tedious, especially as our numbers get larger. So I'm going to draw this next one a little bit differently. I'm going to draw a larger square, and I'm going to divide it so that I have 4 regions, one of them with a larger square, one with a smaller square, and 2 rectangles. The larger square is going to be that x by x, and then for the rectangles, I'm just going to use numbers. If I want 8x divided evenly amongst my dimensions, that means I'm going to be adding 4. So the area of each of these rectangles would be 4x. And because we have 4 horizontally and we have 4 vertically that was added to this, we can take 4 times 4 and get 16 for this lower right corner. So one equation for area is going to be x plus 4 squared. The other way is the total of all of the areas, so x squared plus 8x plus 16. write that a little bit better than I did. So let's do the same thing with this last one. Let's draw a larger square that we then divide into 4 regions. We have our x squared, our x by x square, and we need to divide the 12x evenly. So we're going to have plus 6 plus 6, so that each of these rectangles is 6x. Now 6 by 6 is going to turn this lower region into 36. So when we write our areas, we have a of x equals x plus 6 squared, or we finish what was there, and we have x squared plus 12x plus 36 unit squares. Now if we take a look at these, is there a relationship that you see? Might not be as easy to see with the 4 and 4, but with the 6 and the 9 and the 8 and the 16 and the 12 and the 36? Remember how we had to divide 12 by 2 to get the amount added on? So if I take 12 and divide it by 2, I get 6. And then if I take 6 squared, I will have 36. And that's an important relationship for us. So if x squared plus bx plus c is a perfect square, what is the relationship between b and c? C is going to equal whatever the value of b is divided by 2 squared. So if you're given the partial trinomial x squared plus bx, to find c, you're going to take the b value, divide it by 2, and then square your result. Now, will this work if b is negative? Well, if I take a negative divided by 2, I'll still have a negative, but then when I go and square it, it will still be positive. So yes, it will work, because squaring a negative number results in a positive. Will the strategy work if b is an odd number, like 3, 5, 7? Well, if I did 3 over 2, I'd still have 3 over 2, or 1.5. And I can square 3 over 2, and I can square 1.5. It's just that my result will be a decimal or a fraction. So one of the new customer service representatives that works for Optima thinks she doesn't need to draw diagrams anymore because she found a great shortcut. She writes x plus 5 squared as x squared plus 5. Examine her thinking. Well, if we draw a picture, x plus 5 would be a picture like this. It's not going to work to just have x squared plus 5, because the lower right corner alone is going to be 5 times 5, which is 25. She's also not taking into account the rectangles that are formed by the added length. So yes, she needs to revise her strategy. She needs to add 5 times 2x and 5 squared to the area of the basic square. So what she should have is a of x equals x squared plus 10x plus 25. So can we prove that this works for any square of a binomial or binomial squared? In class, the students chose to do this by diagram, so that's what I'm going to do as well in this video. I'm going to create that basic diagram that has the basic square, and then I'm going to add h to each side. So if we look at the areas of every region, we have x squared. We have x by h. I'm going to write that as hx. We have h by x again, so that's hx. And then we're going to have h by h for h squared. And if we total the area, so if I first write an expression that has each of the areas separate, we have x squared plus hx plus hx plus h squared. And you should recognize that we have two like terms with the hx that we can combine. So we have x squared plus 2hx plus h squared. And I know I wrote it as hx instead of xh, but it means the same thing. So for any time that you are taking the square of a binomial, the middle term is going to be 2 times the hx. The third term is going to be that h squared. If you're someone who has difficulty remembering this pattern, you can always draw yourself a diagram. I call it an area model, and find what your final area will be. So some takeaways: if x squared plus bx plus c is a perfect square, the square of a binomial is going to be x plus b over 2, because we use half of the b value, squared. So for example, if we have x squared plus 16x plus 64 as our perfect square, that's going to equal x plus 8 squared, because 8 is half of the 16. Some additional notation: a binomial is an expression with two terms. Separated by addition or subtraction. An example would be 3x plus 5. I have two terms, 3x and 5, separated by an addition. A trinomial is an expression with three terms. Separated by addition or subtraction. And an example would be x squared minus 10x plus 25. Squaring a binomial would be, for example, taking that 3x plus 5 and squaring it. So as I mentioned at the start of this video, we are practicing the process of completing the square. In this lesson, everything has been a perfect square. So we're able to find that there's a horizontal shift with the parabola if we were to graph it from standard form, because we can write it in its vertex form. The vertex form is going to be a times x plus d squared plus e. We're going to work with this plus e in the next lesson. Here's an example of when a is 1. So this is what we were doing today. We did half of the b and we squared it, but we'll have this additional piece in our next lesson. And then we can identify our vertex, and then we could graph it, because we would also know any stretch or shrink. And then, as some review to wrap this up, find the x and y intercept and graph the equation. So I'm going to put my axes on here first. And we did some of this at the end of lesson 1 as well. I showed you how to graph lines using x and y intercepts in that lesson. Keep in mind, for the x-intercept, the y value of any point is 0. So to find your x-intercept, you're going to replace y with 0 and solve for x. So we have 3x equals 12. Divide both sides by 3, and we have x equals 4, or the ordered pair for 0. For the y-intercept, that's going to be on the y-axis. The x value of any point on the y-axis is 0. So this time we'll take our equation, replace x with 0, and solve for y. So that leaves us 2y equals 12. Divide both sides by 2, and y equals 6. And since we use 0 for x, our ordered pair is 0, 6. And then we can graph our line through those points. Let's see, looks like I need to adjust it just slightly. There we go. And there's our line through the x-intercepts. It is possible, I had this student ask me, is it possible to have x or y intercepts turn out to be negative? And yes, it is possible to have x or y intercepts that are negative. And our last two, each of the following equations has just one intercept. Find it and state whether it is an x-intercept or y-intercept. We talked about in class that when we have a line and the equation is y equals -8, that means every single point on the line has a y value of -8. This means this is a horizontal line. And if it's a horizontal line, it's going to cross the y-axis. So we have a y-intercept at 0, -8, because as we mentioned on the previous screen, when you have a y-intercept, x is 0. And since every single point needs to have -8 as its y value, we know it's going to be -8. When we have an equation like x equals 13, that means all of the x values for any point on the line will be 13. That means we're going to have a vertical line. And we're going to have an x-intercept because vertical lines cross the x-axis at 13, and the y value would be 0. So I had students say, oh, so if you have y equals -8, that's going to be a y-intercept of -8. Exactly, it's not going to be any different from that. And this concludes Lesson 3 from Unit 2.